Hello. So, welcome to our next lesson. We're going to talk a little bit more about conditional probability and different ways of calculating it. We'll determine whether two events are independent. It's going to be our first goal. Calculate and interpret conditional probabilities again, and then calculate just basic independent and union probabilities. So first I want to talk about this, and you may have been wondering this as well. Why does our formula chart does not contain a formula for the probability of A and B? It gives us the probability of A or B, and it gives us the probability of A given B. It does not give us the probability of A and B. Well, technically there is a formula for it, but it's a little tricky and it's kind of a weird one. So technically our formula for probability of A and B is the probability of A times the probability of B given that A has just happened. So you might be wondering why, when we did that pig dice example, did we just do multiply? Why did we not have to think about that given part? Well, technically that given part didn't affect anything. When I was rolling the pig dice, and for example, let's say I wanted to know what's the probability that I roll feet on one roll and back on the next, right? Well, when I multiply that, probability of feet times probability of back, given that feet has just happened, well, those rolls didn't affect each other. Every roll of the pig dice was independent. So the fact that feet just happened is not affecting the probability of back. So we didn't really have to worry about that given part. In other words, the probability of back stays the same on every roll, regardless of what just happened. And the same can be said for flipping coins, rolling regular dice, anything like that, where every single flip or roll or event is independent of the previous one. Technically, for those, I didn't have to worry about the given part because it didn't affect anything. But that leads us to what we call the test for independence. So the test for independence says that if A and B are independent, then the probability of A is just going to be equal to the probability of A given B. In other words, B is not affecting A. So the fact that B is given does not have any effect or change on the probability of A. Probability of A given B is just going to be equal to whatever the probability of A is, because B is not affecting A. And the same could be said the other way. Probability of B would just be probability of B given A, because A is not affecting B. They're not affecting each other, so given doesn't really change that probability. So let's look at an example where we can use that test for independence to determine whether events are independent. So, and this is from the last lesson, so we're just kind of revisiting this concession stand situation. So we have whether or not they purchase food and what team they're supporting. The question is, are the events purchase food and supports the away team independent? So if purchasing food and supporting the away team were independent, then the probability of purchasing food and the probability of purchasing food, given that they're from the away team, those would be equal. If they were independent, then those two probabilities should be equal, because that would mean supporting the away team has no effect on the probability of purchasing food. So let's calculate that. Probability of purchasing food, there's 160 who purchase food out of 250. Divide that, we get 0.64. Probability of purchasing food given that they're from the away team, so only looking at the away team column, 40 purchased food out of 70, which is 0.5714. Those are not equal. So because they're not equal, we can now say that those two events are not independent. Basically, people supporting the away team are less likely to purchase food compared to people at the game as a whole. Being from the away team, it has some kind of effect on the probability of someone purchasing food at this game. So those are not independent. Right? Things to remember about our and probability, right? And this is really what it comes down to be very, very careful. Probability of A and B is only just multiplying probability of A times probability of B if A and B are independent. Otherwise, we have some information that we need in order to find that and probability. We need to know how B is affecting A. We need to be given the conditional probability in some way or another. We need information in order to do that. And if we don't know for sure that the two events are independent, we need to think a little bit more carefully about how we're going to find that and, or if we can find that and probability. Again, examples of independent things that are always independent: rolling dice, flipping coins, etc. Another example would be, I think there was one on your last assignment where it was saying if we have like a large quantity of M&Ms and we're picking M&Ms, when they tell you there's a large quantity, That essentially means each pick of M&M is independent. It doesn't really matter whether you're replacing the M&M or not, because it's such a large quantity and they don't actually tell you what that quantity is. We're assuming each pick of an M&M is independent. So that's another one that would technically be independent. All right, we're going to talk a little bit about another diagram that we can use. This is really useful when we are told the conditional probabilities. So the tree diagram helps us to organize the information in a really useful way that allows us to get to answers a lot quicker. So for this example, tennis great Andy Murray made 60% of his first serves in a recent season. When he made his first serve, he won 76% of the points. When he missed his first serve and had to serve again, he only won 54% of the points. Right? So what we're seeing is that whether or not he makes his first serve is impacting whether or not he wins the point for that serve, right? Because that percentage changes based on whether he made or missed it. So we know we've got some conditional probabilities, and we know we're dealing with a situation that is not independent because that probability is changing. But in order to organize this information, I can use a tree diagram. So I'm going to start with the first thing that happens, which is he's going to do the first serve. So he either makes it or he misses it. Right? It says the probability of making it is 60%. So I'm going to put a 0.6 on that part of the diagram. And then just using my backwards thinking process of elimination, we know that in that case, the probability that he misses the first serve must be 1 minus 0.6, which is 0.4. Then from there, after he makes the serve, eventually he's either going to win that point or he's going to not win that point. And it tells us that if he makes his first serve, he wins 76% of the points. So we know the probability of winning the point in that situation is 0.76. And then again, we can kind of work backwards and say, well, that means the probability of him not winning the point is 1 minus 0.76, which is 0.24. Down here, we have the same two options. If he misses his first serve, he's either going to eventually win that point or not win it. So winning the point happens 54% of the time, so 0.54. 1 minus that is 0.46. So now we have this beautifully set up tree diagram that is kind of organizing that information in a way that's going to be helpful to us, because now we can look at it and see all the numbers. It also helps us calculate our and probabilities, which is going to be really helpful on most of the questions that you're asked with problems like this. So for the sake of quickness, I'm going to let the letter capital F mean that he made the first serve, and I'll use capital W meaning he won the point. So if I wanted to find the probability that he made the first serve and won the point, and we just talked about, if we know they're not independent, or if we don't know they are independent, we can't just multiply probability of first serve times probability of winning the point. However, what we have set up in this tree diagram, right, 0.6 is the probability that he makes the first serve. Technically, this 0.76 is the probability of him winning the point given that he made the first serve. So because of the way we've set up our tree diagram, we can actually just multiply straight across the tree or the branches to get these and probabilities because of the way I organize that information. This is technically our given probability that we need to go ahead and find that and probability. So I'm going to do multiply 0.6 times 0.76 is 0.456. So I know the probability of him making the first serve and winning the point is 0.456. Similarly, I can go through my other tree branch options and get all of my and probabilities. So he can make the first serve and not win the point, which would be 0.6 times 0.24, so 0.144. Probability of not making the first serve and winning the point, 0.4 times 0.54 is 0.216. And then the probability of not making the first serve and not winning the point, 0.4 times 0.46 is 0.184. So now we have our 4 and probabilities. These are the only 4 things that can come out of this situation with these 2 events in particular. So these numbers should add up to 1. So if I add those 4 numbers together, I should get 1 because those are the entire possibility of things that can happen with these 2 events. So now let's get to the questions. So the first question says, on any given serve, what is the probability that Andy wins the point? So we're trying to find probability of him winning the point. And when I look back at my tree diagram that I just made, and I look at my 4 and probabilities that happen at the end, I can see that there's 2 places where he wins the point. He either makes the first serve and wins the point, or he doesn't make the first serve and wins the point. If I just put 0.76, that's not right, because that's technically winning the point given that he made his first serve. 0.54 is winning the point given that he missed his first serve. We want the overall total probability of winning. So we have to go to our ands. And because it can happen in two different places, I'm going to add those two things together. So technically, probability of winning the point would be probability of making the first serve and winning plus the probability of not making the first serve and winning. And I add those two numbers together from my tree diagram that I made, and I get my answer. There's a 0.672 or 67.2% chance of him winning the point overall with all of the things combined. So part B, given that he made his first serve, what is the probability that he doesn't win the point? So if we think back to our notation, the given comes after the line. So the way I would write this in notation is not winning the point, line, so given that he made his first serve. Well, that's something that I actually figured out on my table, right? If I go back to my tree diagram, I can see that given he made his first serve, so looking at that top part of my first event branch, the probability that he doesn't win the point is 0.24. And I got that by subtracting 1 minus 0.76, which is the number they gave me. So I know I've got that one already because I filled out my tree diagram, and that made that a little bit easier. So then part C, suppose you get distracted before seeing where he's first served, but you look up in time to see that he wins the point. So you know he won the point. That is given. So now it's asking what's the probability that he missed. So what's the probability that he missed given that he won the point? Now that's not something I can look at on my tree diagram because given that he wins, well, winning is in two different places. So I don't have like one entire branch of the tree that's just the parts where he won the point. That's not the way the events happen, and that's not the order that the events happen in. So for ones like this, I'm going to have to use my given formula that we learned in the last lesson. All right, so I'm finding the probability that he doesn't win the point that he doesn't make his first serve given that he won the point. So if I go back to my given formula, the given formula says to find that probability, I'm going to do the intersection, so probability that he doesn't make his first serve and wins the point, over divided by the probability of what we're given, which is that he won the point. So probability of the intersection of both things happening divided by the probability of what we're given. And if I go back to my tree diagram and find that probability on the top, don't get the first serve, miss the first serve, and wins the point, was 0.216. And then overall probability of winning the point is what we found up here on part A. That was where we added together the two and probabilities where he won the point, was 0.672. So 0.216 out of 0.672 gives me my answer. So I'm not able to just look at the tree, but I am able to do that a little bit more quickly using the formula because I've already done like the pre-work of drawing out that tree diagram and finding all the and probabilities. Very, very strongly suggest that on problems like this, you take the time to not just draw it out and put the numbers there, but to actually find those and probabilities and label them. Chances are any questions that you're asked based on that information, it's going to be a lot easier for you to answer those questions if you have this kind of pre-work with the tree diagram already done. And it's also a good way to show your work. So on free response questions where you have to show your work to get full credit, this right here is going to show a lot of the work that you would need to show without getting points off later for not doing that. So very, very strongly suggest that you take the time to draw out that tree diagram on any problem, especially free response questions, because that makes sure that you get full credit and it just makes it a lot easier. So we're going to look at last thing, just some more generic probability questions where we're taking the context out of it and looking more at just numbers and rules. So in this example, we are given that probability of A is 0.2 and the probability of not B is 0.3, which then tells us that the probability of B would be 1 minus 0.3, so 0.7. So probability of A is 0.2, probability of B is 0.7. So this says, if possible, find probability of A and B, probability of A or B, and probability of A given B if the events A and B are independent. So let's start with A and B. That's our intersection. Now, as we talked about at the beginning of this lesson, if A and B are independent, we know technically I should be able to just multiply probability of A times probability of B. Technically, it would be probability of B given A. But if A and B are independent, then probability of B is equal to the probability of B given A. So we can just do that. So I'm just going to multiply them. So 0.2 for A times 0.7 for B would give me 0.14. For probability of A or B, we have a formula on our formula chart. The formula says probability of A plus probability of B minus probability of A and B. I know all three of those things now. So 0.2 plus 0.7 minus 0.14 is 0.76. Got it. Probability of A given B, we have a formula for that. Probability of A given B on our formula chart says probability of A and B divided by probability of B. We know both of those things, so I'm just going to plug them in. 0.14 divided by 0.7, which is 0.2. Fun fact, we just now proved that probability of A given B is equal to probability of A as long as A and B are independent. So by multiplying up here to get that 0.14, we made this all happen. If A and B are not independent, we can't do this thing up here on and this thing down here on A given B would not be the same as probability of A. So all of those things kind of work together to make that true. So let's look at that same scenario, but this time A and B are mutually exclusive. So remember, mutually exclusive means that if one thing happens, the other thing can't happen. They are completely separate things. There's no overlap. Basically, what it comes down to is if A and B are mutually exclusive, then the probability of A and B is 0 because they cannot both happen at the same time. So A and B is 0, which means when we go to find probability of A or B, same formula, but again, I'm going to plug in what I know. A is 0.2, B is 0.7, minus A and B is 0, so 0.9. If I'm doing probability of A given B, same formula, but now if I plug in my probability of A and B divided by probability of B, 0 divided by 0.7 is 0. Right? If A and B are mutually exclusive, and it's given that B has already happened, then A cannot happen. That's how that works. Right? So what about if A and B are dependent, not mutually exclusive, because remember, mutually exclusive is technically one form of dependent. So they're dependent, but they're not mutually exclusive. They are affecting each other, but they can happen at the same time. Okay? So in that case, probability of A and B. They're not independent, so I know I can't just multiply. I would have to technically do probability of A times probability of B given A in order to find that and probability. Problem is, I don't know probability of B given A. They have given me no information that I can figure that out with. If they had given me that, I could find it. Easy. I can do it. But since they didn't give me that information, I can't figure this out. It is unable to be determined at this time because I don't know what the probability of B given A is. I don't know how A and B are affecting each other. So I can't do it. Which means for probability of A or B, same formula, but I don't know that third piece. I don't know the and because it was unable to be determined. So I'm stuck. I don't know. Probability of A given B, still same formula, but I don't know this top part. So question mark divided by 0.7, I don't know. So if you're not given any information about how A and B affect each other, I can't really do much. I can't find the and, which means I can't find the or, which means I can't find the given. I'm stuck if I don't have more information about how they affect each other, or if I'm not given that probability of B given A that I would need to find the and probability up here. So that's just a little bit of more abstract with just dealing with numbers. Sometimes we see questions like this more often on multiple choice where they just give you information and ask you to answer certain questions about probabilities, knowing the rules and being familiar with them. All right, that's it for today. I'll see y'all next time. Have a good day.